Welcome to DEEPLIZARD. My name's Chris. In this episode, we're going to learn how to use PyTorch's Sequential class to build neural networks. The Sequential class allows us to build PyTorch neural networks on the fly without having to define an explicit class. This makes it much easier for us to rapidly build neural networks and skip over the part where we have to implement the for method. And this is because the sequential class implements the for method for us. When we use the sequential class to build a PyTorch network, we construct the for method implicitly by sequentially building our network's architecture. A PyTorch sequential module is a container class, or also known as a wrapper class, that allows us to compose neural network modules. We can compose any neural network modules together using the sequential module. This means that we can compose layers to make networks, and we can even compose multiple networks together since networks themselves are neural network modules. Now, interestingly, we can also compose neural network sequential class instances with other neural network sequentials. Ugh, I'm having inception here. We can compose neural network sequential modules together with each other. So we can make one sequential module, and then we can make another sequential module, and we can compose both of those, or encapsulate them both, wrap them both, contain them both, whichever word you want to use, together inside of another sequential module. So these sequential modules are really great for building networks and parts of networks. So at this point, you may be wondering, well, what about operations like activation functions and pooling operations and flattening operations and things like that, which we've seen in the past, in past episodes of the course, that most of these operations live in the neural network functional API. And so how will we be able to have those particular functions and operations be included in our for method if we're composing neural network modules? Well, the cool thing is that PyTorch has wrapped those particular functional, those members of the functional API. Just about every one of them has been wrapped inside of a neural network module itself. So if you're talking about an activation function like ReLU, we can call that function directly through the nn.functional API, or typically known as F. We usually import it as a capital F. So we can say capital F.ReLU, or we can use a neural network module. So in that case, it would be nn.ReLU. And what this is a module wrapper that wraps around the nn.functional API. And what this does is it allows us to create sequential models, and by having the ability to define our layers, our activation functions, our flatten operations, our pooling operations, and things like that. So the main takeaway here is that having all of these functions wrapped up as neural network modules, it allows us to then use the sequential class to wrap multiple modules and compose them together. So we can compose convolutions with max pooling operations, with ReLU activation functions, with flatten operations. And what this does is it allows us to build our models in a sequential way. So there are three ways there are three ways to create a sequential model. So let's jump in and see in code how this would be done with a couple of examples. All right, so I'm here in my Jupyter notebook now, and we're ready to look at some examples. So the first thing we're going to do is start out with our imports. We're going to import all of the stuff that we need. Now, just a quick summary, we're importing Torch. We're importing the neural network package as an in from within Torch. We're going to import the neural network .functional API as capital F. And then we're going to import Torch Vision and transforms from within Torch Vision. We're going to import PyPlot. We're going to import math. We're going to import ordered dict from collections. And then down here, we're going to set our print options with a line width of 150. This is just going to make sure that our output doesn't wrap whenever we're looking at the tensor output. So the next thing we're going to do down here is create a train set to work with, because not only are we going to construct some example sequential networks, but we're also going to pass in a tensor to these networks to get a prediction. So we need a data set for that, and the data set that we're going to be using is the fashion MNIST data set that is coming from the data sets that Torch Vision provides to us. And then the only thing to call out down here is that we're transforming this particular, each image is going to be starting out as a pill image, and then we need to add in this to tensor transformation in order to allow us to transform the pill image into a tensor. So the next thing that we're going to do is just jump right ahead, and from the train set, we're going to access the first member, which is going to be a tuple that contains our image tensor and our labels tensor. So we'll go ahead and get that out, and then we'll inspect the shape of the image, which is one channel, or one color channel, by 28 by 28. The height and width are 28, and this is a grayscale image, so there's one color channel. Okay, so next, let's just use the use PyPlot to show this image, and we can see that this particular image is an image of an ankle boot. This is a particular piece of fashion since we're working in the fashion MNIST data set. Now, the only thing to call out here is that we squeezed this particular image, which took off that particular channel or that particular axis of length 1. So that was in order to allow the image to be plotted. All right, so let's jump down here and just get a little more intel on our training set. So we're going to look here and see that we have 10 classes, all of which are falling into some form of fashion. We got t-shirt all the way down to an ankle boot, which is what this particular sample happened to be. All right, so the next thing is I want to figure out for this particular image that we grabbed, how many elements are inside of the image. So what I mean by that is we're going to look at, we have each element in the image tensor is a pixel, so we have 28 times 28 of these particular values, and then you can also say times 1, but yeah, that's not going to do much for us. But if we had 3 channels, if we were dealing with an RGB channel or with an RGB image, we'd have 3 here, so we do 3 times 28 by 28. But since we're dealing with grayscale, it's going to be 28 by 28. And the way that we actually retrieve that is just to call numL on the image. We're going to set this equal to a variable that we're going to call inFeatures, because we're going to use this particular value to construct our sequential neural network. All right, so we can see here there's 784 pixels, which indeed is 28 by 28. The next thing we're going to do is we're going to set a number of out features for the first hidden layer. So basically, we're going to set the first hidden layer, the number of in features that are coming into the layer is going to be this, the 784. It's the number of pixels in each image. But then the out features for the first, we're going to work with just, we're going to build a regular dense network. We're not going to deal with any convolutions here. So we're going to have to flatten our input first, and that flattened input is going to have 784 pixels, or 784 is its length. The next thing that we need to do is choose a number of output features from that layer. Now, the choice of this is sort of arbitrary, so there's no real like magic formula to choosing this. You can kind of just go with, usually you want to go down, so you don't want to go up in numbers, you want to go down. And so a decent place to start out is to just go with half the number of input features. So if you're coming in with, say, 1,000, then go out with 500. And the idea there that you can kind of think of, the intuition as to why you'd be doing that, is because you're starting with a vector of 1,000 and you want to extract information or some kind of features out of that data. So that's why we typically tend to filter down whenever we're dealing with dense layers. Okay, so this is going to give us 392 output features coming out of what will be our first hidden layer. Okay, next we're going to just get the output classes, which we know is 10, from the train set. we just say classes, and then we get the length of it. All right, so we have 10. So this allows us to have the number of in features coming into our network and the number of out features or predictions coming out of the network. And then in the middle, we're going to have 392 out features coming from the first hidden layer. So now we're ready to take this information and use it to build our first sequential model. So down here, I have the first network. Now, if you've been following along in the course, you're going to like how easy this looks compared to when we had to construct a model through the class way of doing it, where you have to define your own class. So what we have to do is we just say network is going to be a variable. We say nn.sequential. So sequential lives in the neural network package, and this is a class that we are building we're building an instance of this class by passing in other modules in a sequential way. Here they are here, and these define our network. So what this says is the first thing that's going to happen when we come into our network is we're going to flatten the incoming image. And we're doing that because this is going to be a dense network. We're not going to deal with convolutions. So the first step is to flatten it into a single dimensional tensor. And then the start dim says that we want to start flattening at the first dimension. And the reason we want to do that is because, well, let's say this is the second index. So the first dimension is the batch dimension. And so we want to start flattening at the second dimension, which is where the channels live. We don't want to flatten we don't want to flatten the entire batch, because then each image would be kind of concatenated together. So what we want to do is we want to flatten just the individual images. So we're still going to have, if we pass in a batch of say 10 images, when we flatten, we're still going to have the length of 10 along the batch axis, and then the other axes will have a length of, the next axis would have a length of 784. So 10 images of length 784 that have been flattened. So the next thing is two linear layers. The first one is going to be our hidden layer, and it's going to take the in features and the out features. So recall that the in features are 784, and the out features is this arbitrary value 392. All right, and then the next thing is going to be to create our output layer, which is also going to be a linear layer, also known as dense. And the number of in features coming into this one is the out features coming from the previous layer. And then the number of out features is going to be the number of classes, because these represent our predictions. Okay, so when we run this cell, we're going to create the network, and then we're also going to see the output. And then we get that linear layer out. We can say we can see the in features are 784, the out features are 392, and then we also have a bias. All right, so let's see now what it looks like when we pass an image to this network. So what I'm going to do is just create an image that is in batch form. So here we're going to unsqueeze the image, which means add a dimension at index 0. So there it is. We can see before we had 1 by 28 by 28. Now we have 1 by 1 by 28 by 28. This is the number of images in the batch. This is the channels, height, just as a reminder. Okay, so now we're ready to pass this batch of image to the network. It's a batch of length 1. And then here we get back a prediction. So these are 10 predictions for each class. Now, these values are not going to be accurate because we haven't trained this network. So this network was just set up. The architecture was set up in such a way that this particular image could flow through this network. But now if you want to get accurate predictions, you have to train the network. Now, in this case, we're not going to train the network because we're just interested in seeing how to create sequential models. And what we have just seen is that this is the first way. So the first way is to just access the class and then create an instance of the class by passing in sequentially any number of neural network modules. You know they're neural network modules when they're coming from the neural network module package. Okay, so the second way that this can be done is by creating your layers in an ordered dictionary. So that's why we imported the ordered dict earlier, because we're going to use that to create an ordered dictionary of layers and then pass that to the sequential constructor, which is just the second way to do it. Now, the one thing that's interesting about this way is that you can name your layers when you do it this way. So let me show you what I mean. So when we create an ordered dict of layers, we pass in tuples that have first a name and then a module. So here we can say this one's called flat, this one's called hidden, this one's called our output layer. So this is like a flatten, you could call it a flatten module. Yeah, I don't want to call that a layer, but a flatten module. Module's a better word for this kind of stuff. So a flatten module, hidden module, and then an output module. Or these really, you could call them layers. So hidden layer, output layer. And then that's just it. We can pass the layers into the sequential model, and then we're good to go. Let's run this. And then this time we get the same sequential model, but we have, instead of just indices here, we actually have names. So we can access these by name. Now, one thing to note is that these names have to be unique. So if you have like multiple ReLUs, for example, you can't call them all ReLU. So you'd have to go with like ReLU1, ReLU2. So if you want to name them, then this is the way to go. So let's just see that we can also pass this image in that we created earlier and also get 10 predictions. One thing you may have noticed is that the predictions are different. So we can see here for the first prediction, we got this value. Second prediction, we got that value. So if you're wondering why that is, then let's just discuss that now. So the reason that we have the same network, we've created two different networks in terms of code. So in memory, we have two different instances of the sequential class. And so we've named them network 1, and then up here, or this is network 1, and then this is network 2. So we have two different instances of the neural network sequential class. And we could say that these networks are the same because they have the same architecture. But the reason that we got different predictions is because, let me just scroll up so you can see the other ones. The reason we got different predictions is because the way, the way that the networks, the weights inside the network were initialized. So our network's weights are initialized randomly. So this is why we get different predictions, because the weights in the network define the transformation that the network does on the incoming image. We've seen this in past episodes of the course where the linear transformation and all of the transformations in the network via the weights are computed. Now, is it possible to cause these two networks to give us the same prediction upon initializing them? And the answer is yes, but in order to do that, we have to set the seed that the random number generator uses manually. So let's see how to do that now. All right, so you can see that we're doing that here. I'm saying torch.manual seed, and then I'm passing in any given number. So the number here is the seed that determines what random numbers will be generated from the random number generator. And so we have to set this before every initialization. So we set it here, and the reason we have to reset it again when we create the second model is because when the number generator gets used, its state changes. So if we want to get the same values, we have to set it back again before initializing more layers. So here you can see the layers, when they get initialized, their weights are initialized inside. So for this one, the linear layer and both the linear layers have weights that are initialized whenever we run this code. And then down here, when we create, not the flatten, but because the flatten doesn't have any layers, it's just a call, a function that lives inside the functional API that has been wrapped in this neural network module class to allow us to pass it in this way. So it doesn't have any weights, but we set the seed both times, and then the weights will be initialized to be the same. So I'm going to run this code. We're just gonna, in the same way that we did before, we're gonna initialize network 1 and network 2, and then we will run the predictions on those. Again, we'll see network 1 will pass the image, network 2 will pass the image, and then here we can see that both the networks gave us the same predictions this time. Now, there is a third way to do this if you don't like the setup that we've seen so far. So the third way to create the network, basically we can create the same network again in a third way. So I'm going to call this network 3. And what we do is we just initialize a sequential model that we don't pass anything to the constructor. And then after the fact, we can come in here and we can say add module. We pass in the name and then the module. So let's just run this. And then you can see we get the same network, another instance of a network with the same architecture. And just to show you, because we set our seed up here, we're gonna have the weights are gonna be the same. So this network will be starting out from the same place as all the other ones with the same architecture. So we get the same predictions. So this demonstrates the 3 ways that we can use the sequential class to build neural networks rapidly in a sequential way. So we don't have to go through the trouble of defining a class beforehand. We can just on the fly construct networks like we've seen here, and we have 3 options for doing so. Now, just to kind of extend the course that for those of you who are following along in the course, I want to just show you, well, and also if you're just coming to this video and you haven't seen what we've been doing so far, I just want to show you the old way, and then we'll see how to construct. Also, if you're following the course, we'll see how to construct the network that we've already built using the sequential model. So let's go take a look at that. So this is the network that we've built so far in the course, and this was the way that we saw that it was done. You had to have a class definition here that extends neural network module, and then we have to define all of our layers as class attributes. So we have 2 conf layers, 2 fully connected layers, and then the output layer, which is also fully connected. And then we had to manually define our forward function. So you can see here we're manually calling relu after we do the conf, and then we're doing the max pool, and all of this is coming from within inside the functional API. And we even manually flatten the tensor down here. Now, the reason we did this to start with is because it's instructional. It'll help you learn to be able to know how to construct a network in this way. The fact that it's a little more harder and a little explicit makes it more advanced, but it also can give you a deeper understanding of what's going on. Just to show you that this network can be created in this way, let's create it, and then let's take a look at the value that we get back. So here we can see we have all of these particular modules in this network. So now what I want to show you is how to build this same network, which is a little more complicated than our other example, using the sequential API or the sequential class. Okay, so basically we're going to set the seed first, and then we're going to build sequential 1, because we'll do it in all 3 ways, just like we saw. And so the way you do it is just you go through all of the modules that you need. So we're going to start out with a conf layer, and then we're going to go to a relu and then a max pool. Then we go to our second conf layer, a relu and a max pool. Then we flatten, because we're transitioning from conf layers to dense layers. And so we flatten, and again, we're starting at the first dimension because we want to skip over the batch dimension, and we want to start flattening at the channels dimension. Then we do a linear, we do a relu, we do a linear, we do a relu, and then finally we do a linear as our output layer. So this is kind of a concise way to define the same network that we've been working with throughout this course. And then we'll just run this, and then we'll also see to do it the other way if we want to get the same output as before and give names. And so here's where we have to like have relu1 and relu2, but we can go through and we can define an ordered dict as our layers and then create a sequential. And then we can also do it by adding the modules after we create the sequential module. And then down here, I just want to take a look. It's this one with the indexes, this one with the named layers. Again, this last one's going to have named layers. And then finally, because we used the manual seed before we created each of these, we can pass the image in for, oh, and I'm even doing the original network here, defined in the explicit way where we have to actually build our own class. And we can see that each of these networks have the same architecture. They were all built in slightly different ways, and we get the same predictions because we used the manual seed. So indeed, these networks are all the same. So that's it for how to use the sequential class to build neural networks quickly and easily in PyTorch. If you didn't know, we're actually filming this video from Vietnam. So we even have another channel where we document everything that we do on our travels, and we connect with you guys in a new way. So go over to DEEPLIZARD vlog on YouTube and check it out. And also, if you don't know already, check out the DEEPLIZARD HIVEMIND, where you can get exclusive perks and rewards. Thanks for contributing to Collective Intelligence. I'll see you in the next one.